Hey folks, welcome to Study Hall. We're going to get started here. Oops, I'm having a little bit of a lag issue here. Hopefully it'll iron out after a little bit. Cool, yeah. So just want to give folks a quick reminder. The purpose of Study Hall is to give you all a venue to ask us questions. So bring in your Python questions from Learn or really anywhere else. Just throw a link in the thread that I posted on the Basic Prep Slack channel, and I'll take questions from there. Yeah, and if you have any code that you want me to debug, you can throw it in there too. Otherwise, I'll just presume to give a solution, and I'll talk about any underlying concepts that we encounter along the way, and just kind of explore the problem. Maybe look at a few different solutions depending on what's on the table. Okay, cool. So I'm not currently seeing any questions in the thread. Oops. So I think we can just move on into the material. And it looks like last time, let's see, can everything, yeah. So it looks like last time we most recently left off on while loops. So let's just talk about, I'll talk about like where these fit into the big picture here. So I've been doing this thing where we talk about types, functions, conditions, loops, might add evaluation in here as well. And I should really use the proper names for these, the generic names. And iteration. So iteration, we focus on one main type of iterator, and there's two main versions of it. So we focus on loops. In our material, there are other types of things that will iterate over something in various different ways, but loops are powerful and they're simple to use. So generally, we want to use for loops. For loops are powerful, and they make writing code. They make for pretty and simple code that's easy to read, easy to write, easy to maintain, and they get the job done well. But there are certain problems that they're not really meant for. They have certain limitations. Particularly if we need to loop through, if we need to make some unknown number of iterations to solve a problem. In other words, if the number of iterations needed to solve a problem can't be determined before iterating starts, then a while loop is not meant for that kind of problem. A while loop's not well suited for that kind of problem. There are sort of ways of forcing a while loop to work, but you end up with something that looks at least as ugly as a while loop. So we have while loops for this purpose. So while loops are, I think you could say, objectively more powerful in terms, more powerful than for loops in terms of the variety of their application. There's a lot that you can do with them. You can do any problem that you can solve with a for loop, you can also solve with a while loop. But they're a little harder to use. They make for a little bit like kind of clunkier looking and feeling code. They're also prone to getting into infinite loops. I believe I've seen somebody write an infinite for loop, which it can be done, but I believe I've seen it done on accident once. I've done it on purpose, just to say that I know how to do that. So you can write an infinite for loop, but you kind of have to really think about it, or you have to just get really, you have to get into a really particular set of accidents that lead to an infinite for loop. So yeah, in my little over 2 years or so of helping students and seeing people code, I think I've seen somebody write an infinite for loop only once. So while loops, pretty easy to get them into infinite loops. It's kind of their default. Like they're basically going to run until you tell them to stop. So you're responsible for managing the stopping of the looping. Cool. But the trade-off is that they're very powerful and that they can solve quite a wide variety of problems. Cool. Okay. So in the grand scheme of how things fit together, we have different data types, we have different abstractions, which are like, functions, variables, classes. We have control flow, which is conditions, logic, conditional logic. Basically if, elif, else. All the various different types, right? Evaluation is like, the order that the document is parsed and executed in. Statements versus expressions, things like that, right? So in terms of where this fits in, we're talking about iteration today. Okay. Yeah. So unit overview, in general, you should only use while loops when a for loop is not appropriate. A for loop's not appropriate in the circumstance that I mentioned, when the number of iterations needed to solve a problem can't be determined before iteration begins. Under that circumstance, we should use a while loop. So in other words, your default solution, your go-to looping tool should be a for loop. And in my experience, at least most of the problems that most of the times I write a loop ends up being a for loop. So I can get away with, you can get away with that most of the time. And I'll qualify that by saying, I've been able to do that, but depending on the domain of programming that you find yourself in, results may vary. So this unit teaches you the format of while loops and indicates the appropriate problems that can be solved using while loops. Okay. Oops, not that. We'll just go on to the what is a while loop section. So by the end of this lesson, you'll be able to describe the syntax for a while loop, utilize a while loop to solve greatest common divisor problem. Okay. So I'm just going to hop over. I'll keep that up. I'm going to hop over to my editor here. And let's start coding some stuff out. So if you're familiar with conditions, which hopefully you are at this point if you're watching this. If not, I mean, everybody's welcome, but I'll assume some familiarity with conditions, at least conceptually. So, or with control flow. So imagine I have A gets 10 and B gets 20, and I can say if A less than B, print A is less than B. Okay. So we can make this kind of comparison here. This comparison operation is an is an expression that expresses a Boolean value. So a Boolean is what we need here. A Boolean value, true or false, is going to tell this if whether or not to execute the code indented under the body of the if, right? So we need to put code in the body of the if for it to be valid, and then the condition just tells us whether or not we should execute that code. If this condition is false, then we don't execute the code. If it's true, then we do execute the code. So a while loop bears a similarity to this in that while, let's say, while A less than B, it's going to check a condition, very much like an if, and if that condition is true, it's going to execute the body of the while until, so this is where it differs, right? So they're similar in that they check the condition. If the condition is true, they execute the body. That part is the same. The difference is that when an if is done executing the code in the body, it's done. It moves on. It just keeps going. Whereas a while loop, it executes the code in the body of the while, and then it comes back up and checks the condition again, right? So in this case, you're going to look at this and you're going to say, well, it's just going to keep returning, it's going to keep evaluating to true. Yeah, and this is going to be an infinite loop because A is always going to be less than B with code that's written exactly like this. So it's not always the case. There are a number of ways, sort of formula for and different patterns and ways that are suited for different situations. But let's say, for the sake of argument and for the sake of simplicity, really, it's very often the case that you have in your condition for your while, you have one part of your condition that changes and another part of your condition that stays the same. So it's sort of a stator and rotor relationship, like where you have one part that's stationary and one part that's mobile. So that's how I think of it, at least. So we need to modify one of these to change them. So we could do A plus equals 1, right? Or we could do B minus equals 1, right? So yeah, either of these will control the loop properly, right? And let's just look at this. So we'll get a few prints of this when my code decides to execute. It's really taking its time. Really taking. Okay, there we go. Cool. And instead of this silly message, let's just print A and B. We'll just do something like that. So you can see A stays at 10, and then B decrements until it's equal to 10. And then, yeah. So what happens here is B is decremented to 10, and then this says while A is less than B, it's like saying while 10 is less than 10 at this point, then continue looping, right? So since 10 is not less than 10, it's equal to 10, then it's going to stop there and exit the loop. So syntax, let's do a little overview. So we have our while keyword, we have our condition. It's just the same kind of condition that controls an if. If you understand if, just think about a while as an if that continues execution as long as this condition remains true. So that necessitates that something has to change in the loop. You know, there has to be some modification that changes the function, or that changes the condition in the loop. So yeah, let's see. Let's just demonstrate this. Let's say I made an error and I said b plus equals 1, right? So a, while a is less than b, this is going to do the opposite of what I want it to do, because you know a and b are just going to be just going to continue to grow further apart, and there's never going to be a scenario with this code where a is less than b. So it's possible to make a valiant attempt and fail because you made a mistake regarding that. And I can already feel my computer starting to lag. I can see, I don't know if my audio is lagging, but you can see this is going pretty quick. We're already in the 200,000s, right? So I'm burning up a lot of CPU on this. Having a lot of fun here. Let's throw in a break. Oh, there we go. Woo! I feel my keyboard getting hot. All right, that's really doing it. All right, so that'll definitely give you a run for your money. So that's the pitfall with whiles. Is, I mean, they're great. They're, you know, they solve a lot of nuanced problems with them, but you have to manage them. You have to wrangle them, kind of, and that can be kind of annoying, and you can get into infinite loops. And there's certain times where you'll write a while that works for some small variety of scenarios, and then like gets into an infinite loop in some particular case, and you need to handle that as well. So, all right, cool. Greatest common divisor. This is a greatest common divisor problem. So let's look at this. I'm just going to copy in. I'll just copy in the whole thing. Well, I'll just leave that there. And we did cover break and continue. Break, right? So I use break a lot when I'm working with while loops. For those of you who have heard me talk about while loops before, you know I'm a pretty big fan of just saying while true. Because remember, that condition is anything that evaluates to true or false. Well, true evaluates to true. It's kind of like throwing a brick on your gas pedal. You know, it's just going to go until you check some condition. If some condition break, right? So you can have your exit code here. Do whatever you need to do at the end, and then break. Quite often in a function, I'll just return. If I'm in a function, often you break the loop and then immediately return something, so often you can just get away with returning right away. So I like to write my while loops like that quite often. All right, let's paste all this in here. Okay, so we have this greatest common divisors function. So we want to see the greatest common divisors between num1 and num2. Calculate the greatest common divisor of num1 and num2. So runs is this is gonna count the number of iterations we had, right? So this is an interesting way of solving this. So while num2 not equal 0, we say num1 and num2 equals num2 and num1 mod num2. It's a really interesting way to solve this. Huh. Okay, cool. This is a closed formula approach that I'm not familiar with. I would have taken like a totally different approach to this problem. Gone through, probably made a list of divisors for each one, and then found the largest one that's in both lists. That's what I would have done, but clearly this works. Hopefully that works. And it's a very elegant solution. I wonder if they're going to talk about why this works this way. Okay, there are various algorithms that you should be able to write offhand. The GCD function is one of those algorithms. It's a good candidate for using a while loop since different pairs of numbers will require different numbers of iterations to solve the greatest common divisor. The greatest common divisor of two numbers is the largest integer that evenly divides into those numbers. Analyze the following code to understand the algorithm. Notice that depending on what numbers you pass in as arguments, the loop will run a different number of times. Cool. Yeah. So we could go through and like poke around here. Try to understand this algorithm. Let's just start printing things off. Num1, num2. See what that gives us. I'm going to actually indent this in the output so that I can tell what's being printed there and what's being printed on the outputs here. Well, that's really interesting. Okay, so we start with 121 and 55, and then it looks like, so this first operation, I notice we just we sort of move num2 over into num1. So we're sort of moving, there's this kind of constant moving of num2 into num1, and then we assign num2 to the remainder of num1 over num2. The remainder of num1 over num2. So yeah, let's look at this. We start with 75 and 50. This looks like a good one. So this one, I mean, I just know this in my head because I know 25 is a factor. It's the greatest possible factor of 50, and it's also a factor of 75. So this is an easy one. So if we do, oh, that totally makes sense, right? So the remainder of num1 over num2, the remainder of 75 over 50 is 25. And then, so we move that 50 into num1, and then 25 and 0. So the remainder of of 50 over 25 is 0. Well, that's a pretty brilliant and simple way of solving that problem. So that's pretty cool. So it gets that remainder and pares that down, and that remainder will sort of shrink down until we find our greatest common factor. Yeah. What a really cool way to solve that problem. Cool. All right. So challenges. So true or false, only use while loop when the number of iterations the loop will require is unknown. True. Absolutely. Pretty well said. Nice and succinct. What condition does a while loop check to see if it should keep going? I don't know how I don't know how I feel about this is the way this is worded. A condition is a statement or it's an expression that gives back a value of true or false. It's something that evaluates to true or false, including the value true and the value false are expressions that express their own values. So that's like asking what condition does a condition check? I don't know. So what condition does a while loop check to see? Maybe this is asking like what's the nature of the condition? So this is a Boolean statement declared at the beginning of the while loop. A stopping condition inside of an if-else block inside the while loop. Yeah. A counter over a range of values, much like a for loop. Nope. Or none of the above. Honestly, I would say, based on the way that these are written, this first one has a number of ways of being interpreted. The second one is a valid way of controlling a while loop, but I guess it doesn't match this question. What condition does a while loop check to see if it should keep going? So a Boolean, I would say expression declared at the beginning of a while loop. I mean, I don't know. I guess that's close. Yeah, okay, good. I might go back and edit the copy of this to make this a little clearer because I'm not sure how I would feel about that. Let me just Slack this link to myself while I'm thinking about it so I remember. Well, someday Slack will load, and that'll be great. Okay. It looks like I already have solved this one. So use a while loop to fill in the find primes function below. Feel free to utilize the predefined IsPrime function. I guess they give us IsPrime. Oh. Is IsPrime just defined in this code for us? That's interesting. Oh. Is that going to run like that? I think I need that IsPrime. Oh no, I'm silly. This is literally the predefined IsPrime function right here. Okay. IsPrime. Okay. So this is an interesting way of writing an IsPrime function. I usually might write mine with a for loop, but I guess this is a way of doing it with a while loop. So if x is equal to 1, we're going to return false. If x is equal to 2, we'll return true. And then for this, we've got test equals x over 2, while test is greater than or equal to 2. If x mod test oh yeah, okay. So if x over test has a remainder of 0, it's not a prime number. Otherwise, we're just going to decrement test. And then this will, if we make it all the way through that loop, will return true. Woo! What a weird way to write IsPrime, in my opinion. So I'm actually just going to copy this in, write my own IsPrime function. You can decide which way you like better, I guess. Although my way is objectively the best possible way, so, Okay. So I'm going to do def IsPrime. And this is going to work basically the same as the other IsPrime. I'm just going to, I don't know, just do it my way. So def IsPrime will take in n. We'll say if n is less than or equal to 1, return false, else, actually we don't need an else, I'm going to say for I in range 2 to the square root as an int plus 1. Okay. So you don't have to do the square root. You could just do 2 to n and not include n. You specifically do not want to check n because, n is divisible by itself. Any number is divisible by itself, it equals 1. So we start at 2 because we don't want to see if we're setting ourselves up to do this line down here. If n mod I, so if n over I has a remainder of 0, that's what this line's about. Well, here I'll just return false. Right. So the reason we can pare down the numbers that we need to check down to n, or excuse me, down to a range of 2 to the square root of n. Yeah, plus 1, including the square root, because it's possible that a number has that a number is a perfect square, which means it has a whole integer that squares into that number, but has no other divisors. I don't know of such a number off the top of my head, but we want to include the square root to accommodate that eventuality. I'd be surprised if that doesn't happen. So this is the smallest possible set of numbers that we could check. And actually, as I think about it, I think we could even do this. We could go, no, we need to check 2, and then we could do, shoot, there's a way of doing this where you check like every other number, but I don't know. I need to like iron that out again. But yeah, just to be clear, you could do either half of n and include it, or you could just do n and not include n, and that would work as well. This is just really an optimization that I like to make, but that you don't have to do. Okay, so there's my nothing there. And then we can return true. So if we make it, again, it's same sort of logic as this other IsPrime here. You know, we're sort of handling some edge cases up front. I'm handling those differently. And then this is test instead of I, but it's essentially the same thing. And they're just doing half of x, which is fine as well. And decrementing, I'm going to be incrementing from 2 to my upper bound. They're decrementing from their upper bound down to 2. But yeah, basically if we find a divisor, we're going to return false. If we don't, then we're going to make it through the loop and return true. Okay, cool. So find primes finds all the prime numbers and potentially up to and potentially including an input number. So this is going to be pretty straightforward. So in is I see. I was thinking this was a different problem in Learn. There's another similar problem like this that takes a list. So let's see, finds all prime numbers up to and potentially including an input number and returns all the prime numbers. So what we can do for this is list equals an empty list, and we'll say, oops, for I in range. Now I don't want to start at 0. I could start at 1, but there's no point. 1's not a prime, so 2 is the smallest prime. We'll start checking at 2, and we'll go up to and including n, that's n plus 1. Then we'll just say if IsPrime I list dot append I and turn list. There we go. Cool. I'm just going to do this business. Oh, not the whole file. I don't really want the whole file. I'm going to do this. I'm going to submit my own IsPrime function because I don't know. I like my IsPrime function, I guess. Cool. Oh, I was supposed to use a while loop because we're literally on the lesson about while loops, and I used a for loop instead. So in good faith, I'll use a while loop. I'm just gonna do this. I equals. This is actually good though. It's good to see, you know, what while loops are really capable of. So I'll say while. I'm gonna start I at 2. I'm gonna say while I is less than or equal to n, and that the equal part will mean that it will include checking n. And then once I is incremented and greater than n, which I have to do, I was thinking, okay, that's just going to happen automatically. I'm really good at avoiding while loops. I tell you, I've made it into an art of avoiding while loops wherever I can. And someday you will be too. Okay, so while I is less than or equal to n, I plus equals 1. The way I have this written, I think it kind of makes more sense if I do this last. I really do like to do my incrementation like first thing in the loop, you know, so I'm actually going to do this. I'll start it at 1, then I'll increment it immediately. So that means the first number I'm actually checking is I. And then let's actually have a test here. And I'm going to test for I in range 2 to, we'll do 2 to 8, so we'll check 7, and we'll print find primes of I, right? So I'm doing, basically this is my way. Well, I could just simplify this down and just do 2, 3, 4, 5, 6, 7. Actually 7. It ends at 7. So that's what's happening here. I'll just take it out of the loop. Well, yeah. Instead of writing this, I'm just writing in a loop. I'm actually going to leave it in the loop. I know I'm being indecisive. It's okay. Looks like you got a comment here. If the range starts at 3 and steps by 2, I think only odd numbers are checked. Yeah. Which I guess that's what we want. But the problem is, I guess it would allow even numbers through. Wouldn't it? Yeah, because like a number like, if I'm checking 10 and I check all the numbers between 3 and the square root of 10, it's going to make it look like 10 is prime. 10's like a weird, it's a weird even number. It's like if there were such as a thing as even prime numbers, 10 would be an even prime number, right? Because it's divisible by the fewest possible things that an even number can be divisible by, which is 2, some other number, 2 half of 10, and 1 in 10 itself. So I think that's why I didn't do it that way. I have written it that way before, like where I started to, oh, I remember. Yeah, I remember now. I have to check it here. I have to just make a special case for it. So if, we'll say or in mod 2 equals 0. So under both of these conditions, I'll return false. Now I can start at 3 because I got to check that 2, and then I can take steps of 2. Okay, that is an efficient IsPrime. I think that is about as efficient as it can get. There's probably somebody's got a really sweet formula that will bend my brain into the melting point, but yeah, that's a nice IsPrime. Okay, cool. So let's run our find primes. Good comment, by the way. Okay, so it looks like, let me print out I along with this so I know which number is being checked. Aha, as I suspected. So it looks like it's checking one more than the, so it's saying 7 is a part of, is a prime number within the range of 6. And that's not the case. And it's actually also missing 2, which is very interesting. So perhaps did I break my IsPrime function? Very, very interesting. Because 2 should be prime. Oh, right. Yeah, I did break it. I broke it specifically for 2 because 2 mod 2 is 0. And that's the only exception to this. So I might even take another edge case and just get 2 out of the way and just say if n equals 2, return true. So if n is 2, we know it's a prime number. Otherwise, for any other case, if the number is divisible by 2, it is not a prime number. The only exception to that is 2 itself. And then for I in range, okay, there we go. So that fixes one problem. So we had a problem with our lower bound and our upper bound. So that should fix our lower bound there. Yes, that does. So that gives us 2. Good. And now we got to fix this with, you can see 5 is included for 4, 3 is included for 2. You know, so it's checking one number too high. So I can just adjust that by saying I less than n, and that should solve that problem. Okay, so 3 is included for 3, 2 and 3 is for 4, 2, 3, and 5 is for 5, 2, 3, 5 is for 6, 2, 3, 5, 7 is for 7. All right, okay, cool. There's our better version of this, or our version that uses while loops, even when they're not necessary. You know what? I'm going to keep my for loop solution in there. Oh, you know, I should actually test the I should test the while loop code, because, you know, that's what the point is. If I don't test it, it doesn't work. And I just went back because Google Chrome has all the shortcuts. Just trying to scroll around and it's like, did you want to go back a page? No, I didn't. Okay. Well, let's get back to this. Okay. Correct. It worked. Good. Do we have more with this one? A little issue there. All right, cool. That was a fun one. I like it when I kind of get to explore around. Kind of like, this IsPrime function is just really nice. I'm really happy with it. Okay, cool. So we do have a question in Slack here. Tab at okay, there we go. So output sum digits is 14. Is this because that's 12 plus 2? Oh, and I'm wondering, oh, yeah, okay, I think I remember this one. So 6 plus 1 is 4. 6 plus 1 is 7. Okay, 6 plus 1 is 7, minus 3 is 4. The first number gets treated as a negative 1, or as a negative version of itself. So I remember this. Let's just start off. What do I get if I print, if I do digits equals string n, and I print digits? I guess I could have just printed stir n. Okay, I know what I'm going to get for this one. I'm pretty sure I get the negative sign for this. I do. Okay, good. So all you got to do is loop through. We'll have a Boolean latch because those are fun. So for digit in string of n, and then we'll do this. Latch equals, I'm just going to start it at false. I might need to change that, but I'm not really even thinking about it right now. And then we'll say if latch and we want to return, wait, what do I want to return? Digsum. Return digsum. Okay, digsum equals 0. So if latch is true, we're going to digsum minus equals dig. Minus equals dig. Else, hey, come on. Else dig sum plus equals dig. And then we need the logic to turn. All right, yep. So if dig equals a negative, then latch equals true. Right, and I can't do this because I've got to reset latch here. False. Okay, let's just do this. Quit with the fancy pantsiness. Okay. Okay. So there are other ways to approach this. I could see if like the first if in or if stir in sub 0 equals a negative, then we could do something like continue, and then, well, we still need to carry that information to subtract the first number, which the answer to that for me is always a Boolean latch. So this is kind of a funny little pattern, and so admittedly I didn't learn this pattern. I discovered it just from doing it a lot. In my head I've always called it a Boolean latch. I know there's like latching logic and stuff, so I might actually be using that term wrong, but I've always called this pattern a Boolean latch. So if you know better and you know that that's not what that's actually called, then you can feel free to let me know. But for what I know, that's what I call this. So basically what's happening here, we start our latch at false, and the way I think about it is like on one go around it checks a condition and flips the latch. So we flip it from true to false. And then on each turn the latch is checked. It's a Boolean, right? The Boolean latch is checked as its own condition somewhere, right? And then if it's true, you reset it to false and do something. I've detected something in one iteration that tells me I need to do something special the next iteration. In this case, I detected that dig was equal to a minus symbol, which tells me that the next iteration, the special thing that I want to do is dig sum minus equals dig rather than dig sum plus equals dig, right? So, and then in the latch true channel, and I said this before, but I just want to reiterate this. In the latch true channel, you set latch to false, or you reset latch. So I'm not sure if it's always that you started at false. I kind of think it is. I don't know. I'm not going to commit to that, but I think I probably end up usually starting it at false, checking the switch, let's call it the switching condition. This is the condition that I should switch latch under. and then checking the latch. And if the latch is true, we set it to false, so we don't keep doing it. If we don't reset it to false, we're just going to keep minus equaling dig. So yeah, so that's a Boolean latch. It took me a lot of painful times of like figuring. It was one of those things where it's like every time I had to like do something next iteration, I was like, God, how do I do this? I have to figure this out every single time. And then I kind of noticed that there were some similarities and things that I was doing, and ended up playing around with it and sort of formalizing this idea. So, or at least semi-formal. Nope. And it doesn't work. After all that, it doesn't even work. No. Okay. I'm not seeing any other questions coming in. Let's just see here. I think I want to give folks a minute to just, if you have any questions, feel free to bring them in. I'm just going to hang out for, put a minute on the clock and just see if we can get a couple questions in here. All right. Not seeing anything. That's all right. We can move on. Oops. My computer going to be responsive? Okay, cool. So next section is on infinite while loops. So I think I kind of demonstrated that. What it means to get, oh, what's going on here? Man, this is being slow right now. Okay. Yeah, I mean, this is somewhat of a problem when you're working with code that has while loops in it. It's code. It says I can run forever. It should say I will run forever in that form. That while true, like I said, it's like throwing a brick on your gas pedal. It's just gonna keep going. Yeah. So this is this is another one of those things. I remember figuring this out after being a beginner for several weeks and kind of arriving at this, like, oh, I could just set like an arbitrary upper limit on my while loops and then break them manually uh, if they go over a certain limit, because a lot of times, like, you don't know how many times you need to loop, but it's not going to be more than however many. Maybe it's like you're not sure how many loops, but for your particular purpose, it's never going to be more than 100 or never going to be more than 50,000 or something. So you can pick an arbitrary upper bound. So this is just sort of creating that loop counter here. So if we just do like limit, let's do counter. Let's call it counter equals 0, and then while this is actually a good example, right? So I equals 0 while I less than 10, print I. I'll comment that out for now, and then I'm going to say counter plus equals 1, and if counter is greater than 200, just break. So this is my emergency break. Right, so I know whatever I'm doing in here, I can just have this safe stop to my while loop, so it doesn't just run forever and I have to like stop the thing that I have to do, cancel the program or whatever, which is not that hard to do, but like if you're, I don't know, I have a lot of funny, when my first attempt at learning Python, let's say that, they taught us, this was not at Galvanize, this is somewhere else, but they taught us while loops without mentioning that for loops exist, and yeah, that's the reason I don't do that. Because for loops are so much easier. So if we look at this code, we can see that this condition is going to be false, right? So we start I at 0 or wherever we start it. We can print it off, and we can realize, oh well, I is never being incremented, so this condition will never be false. Yeah, so this portion of the code will act as our emergency brake, and if we wanted to just set like a limit of 2,000 or something, space to like explore whatever problem that we're working on, but we're not going to have to worry about getting into an actually infinite loop. Okay. So yeah, this is a we're trying to put these, kind of sprinkle these around. Remember, if you get stuck, you can always find help on our Slack channel, our Slack workspace. If you haven't already joined Slack, you can do so there. But of course, everybody in Slack is in Slack. All right, so when working with a while loop, it is good to blank before running the code. Make sure the loop body is complete. Build an exit condition. I'd say build an exit condition. Why not? Like if you're at the initial writing, cool. Which statement is true about whether the following code block will finish? Yes, the loop will terminate because the while loop condition will become false. Okay, so number mod divisor 1 has to be not 0, and number mod divisor 2 has to also not be 0. So I do see divisor 2 equals divisor 1, divisor 1 equals tempvar equals divisor 2. So it looks like these just get swapped here. Yeah, so ultimately divisor 1 has divisor 2's value. So these just get swapped back and forth every time. Number doesn't change. Oh, but number 2. Oh, loop counter. So if loop counter is greater than 10, break. And then if you look here, we got loop counter times equals 1. Since loop counter is starting at 0, if we do, this is like saying loop counter equals loop counter times 1. 0 times 1 is 0. So loop counter is never going to break the loop. And then this is just going to flip-flop divisor 1 and divisor 2. So I don't know, I suppose that there's yeah, okay, no. This. Yeah, actually, both of these are always going to, so what's going to happen here is it's going to check by each divisor. And it's just going to flip-flop between those. So there's no case in this specific code with these specific values where either number divided by either one is going to be 0. It'll never be 0 is what I'm trying to say. And the same can be said about number 2. So number 2 over divisor 1 or divisor 2 will never be, is not 0. So that's true. And number 2 over divisor 1 or divisor 2 will also not ever be 0. So that's also true. And since these are just being flip-flopped, nothing's going to change. So like I was saying, like at the beginning, I was like, you know, there's something you should change, or it's often the case in a while loop condition that there's something that changes and something that stays the same. Well, number and number 2 stay the same, and divisor 1 and divisor 2 do change, but they just change back and forth between each other's values, so it's kind of a moot point. So yeah, okay. So let's see what's true about this incredibly silly code. Yes, the loop will terminate. No, it won't. Yes, the loop. Nope, it won't. Yes, nope. So no, the loop will not terminate because neither the loop of the stopping can okay. No, the loop will not terminate because neither of the loop stopping conditions will be met. Yes. So because the parameters divisor 1 and divisor 2 are switching back and forth, never actually changing meaningfully, the conditional in the while loop definition in the loop head won't ever be false. And because multiplication is used instead of addition, the set is always going to be 0. Okay, so which of the loops below, loops, would run infinitely? X less than 100, x starts at 0, plus equals 1. Okay. Okay, it's going to be x equals 120. While x is greater than 100, we decrement x by 1, so that'll eventually count down from 120 until it's less than 100, so that'll exit as well. So option C here, where x is equal to 100, and while x is greater than or equal to 100, we're going to add 1 to x. So x is just going to get further away from the condition that it would stop under. Okay, cool. We got about 10 minutes left, so I'll just do, it seems like people don't have questions at this point, which is okay. I don't mind going through the material, but yeah, I'll just do a last call. If anybody has wants to get one in there, we might have time for one or two. All right. So conditional check. So utilize the conditional check in a while loop. So let's see. So while loop using a conditional check. Although there are occasions where you will write, or where you will use the while true do something construct. In most cases, you will use a conditional check at the initialization of the loop. So this is just saying to use this, to check this condition in the head. That's what it's talking about here. And I think in previous material, and I often will sort of drive people at doing things like this. And honestly, it's generally my preference. In some of our previous material, I think we talk about while true like this. I was showing this a little bit ago. I I generally prefer to do this. I mean, generally I'll just do whichever comes to my mind first. If the condition is obvious to put up here, a lot of times I'll just put it in if that's how I'm thinking about it. If it's not though, usually just to keep myself moving forward, I'll just say while true, and then get into the problem logic. And as usually I get a couple lines in, and I realize, oh well, if I check exit condition, whatever, then break. So usually this is more forthcoming to the way that I think than this. If you do things this way, you end up checking the inverse of the other condition. So if I wanted to do like I equals 0, well, I less than 10, I plus equals 1, print I. So if I wanted to rewrite this as a while true, right, so that'll go from 1 to 10 like that, I would have to, instead of doing while I less than 10, I would have to say if I greater than or equal to 10, right? So I have to invert that condition. I can also just do something like not. So while not, or if not I less than 10, break. So when you're doing a while true, you get to check the opposite condition. And in general, the way I think about this is, if I is not less than 10, or if I is greater than or equal to 10, this tells me that I've achieved the value of I that I'm looking for. A lot of times you can do that, right? Like you can tell if you've found what you're looking for easier than you can tell if you haven't yet found what you're looking for. You know, so if you check in the loop head, it's while not success loop. If you do a while true and check in a condition, it's if success stop looping. And to me, if success stop looping as a paradigm is just generally, I don't know, more forthcoming. But this way of doing things with the more conventional way of doing things like this, these loops are equivalent. And my preference is generally the first one. Doesn't really matter though. It's 6 of one, half a dozen of the other kind of thing. Okay. This way is more formal, but I still kind of stick to my preferred way. Whatever. So in most cases, you'll use the conditional check at the initialization of the loop. Notice in this example that I for how many iteration times the operation should occur. That's true, yeah, and in these examples as well. However, this format was chosen in order to simplify the demonstration of the while loop. Here you use a while loop to, after every order, the code to see if another assigning continue, right? So this is the thing that's changing. This is still fits that pattern, right? Continue changes, y stays the same. There's various things you can do. Here, let me actually just copy this in. Not sure it totally makes sense with this particular case, but in some cases you can do this cool thing where, let me just shrink that down, where you can take input right in the loop head like this, right? And then we don't need the continue. You can just do that, right? So input order more. I would probably say yes or no. And then we'll just say dot lower, standardize it, make sure that we're checking lowercase version, right? So we'll take in input right here, and if it's a yes, then we'll call get menu item, which will ask for input 1, 2, or 3. Let's just run it. Okay. Oh my gosh, it's being so slow. Order more, yes. Carrots. Order more, yes. Broccoli. Order more, yes. Cabbage. And then order more, no. There we go. Carrots, broccoli, cabbage. So just another variation on that. Let's just look through here. See what we've got. Fibsec maker. Okay. We're getting into some other kind of functions here that I think are worth diving into. So I think we'll go through this stuff next time. This is basically our normal stopping time. So we can just wrap up here. But yeah, thanks to the person who brought in a question today, and the other person who made a comment that helped me or encouraged me to write that better IsPrime function. That was a fun one. So yeah, thanks for everybody who attended, and go ahead and give us a like and a subscribe on YouTube. That does help us out. And I will see you for next study hall. Yeah, take care until then.